Okay, welcome back to this part about implementing a Visual SLAM system based on the LDSO. We have left off at the dataset reader, and here we have a few to-dos. That is to include various header files, which we will try to create and implement in this part today. But before I begin, I have got a comment on the YouTube video by Maxime. He asked if I could upload the code to GitHub. And of course I did that. So you can download the current version of the code when you go to my GitHub profile. It will be linked in the YouTube video, and it's also linked in the Twitch channel, and there you can follow the progress. Okay, let's go back to the code and let us take a look at what we have so far and where we need to continue. So first of all, what we did in the last part is we have implemented the traversal of the directories and parsing of the files, parsing of the arguments, and so far we can step through all the files we want to load. But what is actually missing is, for example, for the pre-image item, the data type image and exposure. This is the data type we want to implement hopefully today or in this part. But for the image and exposure type, we need a little bit of preparation. That is, for example, we need to implement not image and exposure, but we need to implement what is called the minimal image. I think it's used here somewhere. Let's see. Yeah, like here, for example, there's a minimal image B, which is necessary. And when we have the minimal image B, we have the image and exposure, or we can implement the image and exposure. And with the image and exposure, we can implement the undistorter. And this undistorter will be like the first part or the first logic that will take our images and apply some basic Visual SLAM magic to it. That is, work with camera models, the camera intrinsics, the camera calibration as it's also called, and transforming the pixels. What that is, we will discuss that. I don't think we will do that in this part, but we need to do the preparation stuff first. Okay, so let's see. What are the includes that we need? There are two includes from the internal directory, that is GlobalCalib and GlobalFuncs. We will start with that. Why? Because GlobalCalib will be used in the image data type and mostly in the undistorter. And the GlobalFuncs will also be used later. And when we are tackling the internal directory, I would say we just finish the global stuff and then we continue with the image related stuff. Okay, so let's create the directory. Here in this include directory, we will create another directory, right click, new folder, and that will be the internal folder. In this internal folder, we will create a new file that is called GlobalCalib.h. And that's this one. Now, we will also create the next file, that is the globalfuncs.h file. That's this one. And we will start with the GlobalCalib header file. As always, we will create a pragma once, that we want to include the file only once. And then we will start with the if defined or if not defined LDSO Twitch, I think, let's see. Yes, LDSO Twitch GlobalCalib.h. If this is not defined, then we want to define it. And in the end, of course, we want to end if this header guard. Okay, here we will include another file that is called, or that will be called, NumTypes.h. This file will contain various numeric types that we will use throughout the whole implementation. I will get into more detail when we start to do that. And the other file will be a settings.h file that we already have created last time. Next, we'll define a namespace, which is called LDSO. I think I have left it with LDSO. Yes, okay. So we will not alter that to LDSO Twitch. We will leave that like it is. And next we will create another namespace, which is called internal. So in this way, we have this kind of scope operator, LDSO, and then internal. If we want to access something inside this namespace, this nested namespace. Okay, what is included here? We are in the GlobalCalib.header file, so we need to add something related to calibration. And what does that mean? Usually we have images. Those images have a width and a height. And they also have some other parameters like a focal length and a principal point. These values here define what is called a pinhole camera model. And this is what we try to modify our images to follow or to be defined using this pinhole camera model. So we need to store the variables as I just wrote here, the image dimensions and so on. So we define an extern integer, and this will be the width, and then G for global, and then we will have a variable that was defined in the settings that is called pyramid levels. It's not exactly the same with this pyramid levels, but this will be a local variable, I think, that will be defined now no, sorry, that's wrong. It will not be defined in this file. It should be actually the same pyramid levels that's defined in settings. I don't know why it's not recognizing that. Okay, so here in the settings file, we have the pyramid levels, which is set to 6 by default. And these pyramid levels define how many images we have in this pyramid. So basically, if we have 6 pyramid levels, we'll have 6 images. So if we load in an image from the file system, this image will be duplicated 6 times with different resolutions, and therefore also with different focal lengths and different principal points. And that's what we need to define here. So we define the width and the height as global variables. Pyramid levels. Okay, let's save that. Okay, settings can be found now. We continue with another extern. This time it's a float for the focal length. That is fx global. And then number of pyramid levels. And fy global. Number of pyramid levels. And then there's the principal point, which will be called cx global for the pyramid levels again, and cy global, and also number of pyramid levels. Let's write it like that. So we have the image dimensions here, and we have the pinhole camera model here. Next, we need to have definitions for the camera model with, I think, integers. Let's see. Let's write extern, but still float. And then the same as we did here, but we add an I after each kind of parameter. And we will see what that means when we take a look in the implementation file, so into the CC file of GlobalCalib. Okay, next we have another extern. This time we have the eigen data type. That is a matrix 3F. So it's a 3x3 matrix as a float parameter or with float data types. That is kg and number of pyramid levels. And then we have kig of pyramid levels. Now I think the I could in fact mean the inverse. I'm not sure at the moment. We'll find out soon. But I think there is a non-inverted version and an inverted version. Why? This will be important during the evaluation of the math, because sometimes we want to project 3D points into the image plane, and sometimes we want to back project or unproject, or like basically transform from the image plane into camera space. And this is done using the inverses. Okay, next we have extern float. WM3G and extern float HM3G. Here we have a comment with W-3 and H-3. Not sure what that means at the moment, but this should get clear in a minute. Then we have a function where we can set each level's calibration. This will be a void, which is called set GlobalCalib, and it will take in an integer for the width, integer for the height, and a constant eigen matrix 3f. We pass the reference, it's actually called by name, with a k matrix, which will be our calibration matrix. So given these three parameters, we'll set these global ones here. This will be helpful to access the global calibration for each pyramid level across the files that we will create. Okay, that's it for the GlobalCalib.h file, and of course you have noticed we have a problem here. We need the NumTypes header file. Okay, let's create it. So new file, we'll create it in the include directory. So in the top directory in the include folder, and call it NumTypes.h. This way, this error should be gone, at least in a minute. Let's so far work with the include guards. So once again, we will add a pragma once. Then we will add an if not defined LDSO Twitch NumTypes.h, and if it's not defined, we define it, and in the end we will have the end if. Okay, it's still not finding that, unfortunately, but maybe in a minute. What we'll do in the NumTypes.header file, we will first import some numeric types. We have quite a lot of them. We have many numerical types that are needed in the LDSO. First of all, we have to include the eigen types. That is, we have the eigen 3, and we have eigen, and we have core. And next we have eigen standard vector. What is this useful for? Usually eigen will provide us a lot of types for linear algebra, that is vectors and matrices. Next we will have another library that we need to include, and that is called Sophus. The name comes from Sophus Lee, who has invented the Lie algebras. So there are Lie groups and Lie algebras. Lie groups can be seen as matrices, and Lie algebras can be seen as vectors. And the Sophos library will provide conversions between those two types. And there is one specific type, which is the special Euclidean group, se3.hpp. And there is also a sim3 group. There's also SO3 for special orthogonal group, and sim is for similarity. Those data types will be used for poses. So that is pose consisting, so basically let's say a camera pose consisting of translation and rotation. And here we have a camera pose consisting of translation, rotation, and scale. We do not have the Sophos library at the moment, but this is included in the LDSO, in the original LDSO code, so we will copy that. Let's see here, we have the LDSO, and in the LDSO we have a third-party folder, and here we have Sophos, and we will also create this, or copy this Sophos config CMakeIn file. This will be necessary, I think. Let's copy that to our file, third party, and let's move it here. Okay. Let's see, we save that. Okay, something's wrong. Let's try to compile that with this make project command. Okay, so far no errors. Okay, let's still continue. I'm not sure why this file cannot be found. Okay, there's a problem with eigen, it seems. Okay, but until we do not have some compile errors, I would say we will continue. Next, we need to include the memory library. And then we will use the namespace, a standard namespace. Then we will also include the Google logging file or Google logging library, glog logging.h. And we will also include the bag of words library, debo3/source/debo3.header file. Okay, now we can go ahead and define the data types that we need. That is, we need to define some pose data types. And the poses are represented as Sophus structs as follows. In Sophus, we have data types such as SE3, and we have a D and an F variant, that is a double and a float. We'll use the doubles due to the higher precision. And we want to map this cryptic Sophus SE3D to SE3. And we do that using a type def, like this. And we do the same for the SO 3D type, and we name it SO3. So that is a special orthogonal group. SE is special Euclidean group, and we have type def Sophus sim3D, and we call that sim3. Okay, next we will have some camera intrinsics. That is fx, fy, cx, cy, and that means we have 4 parameters. And for the following, please note that the types below, which have C included in the name, mean camera parameters. That means camera parameters. So first we define a constant integer for the number of camera parameters, C parse. That is equal to 4, because it's fx, fy, cx, and cy. Then we define another integer which tells us how many, or what the maximum residuals per point are in our case. And these are 8. And this number of residuals is defined in each point. And we can see the paper of DSO's paper for the pattern. What that means is we can take a look at the paper here for direct sparse odometry, and we will see that in this paper, a few pages later, here the residual pattern is introduced. And this is similar to what we have defined, or this is exactly what we have defined in the settings. If we take a look back here into the settings.h file, somewhere in the end, oh, it's in the implementation. So settings.cc. Here we have those static patterns where we define a pixel grid and we define what kind of pattern we want to have around a specific feature point in the center. And somewhere below, I think it should be pattern 9 here, which is the one that is defined in the DSO paper. And the DSO paper is this one, and this is this residual pattern. So later what will be done is around the center pixel we want to read all the neighboring pixels here, and calculate what is called a loss or an energy that is used during optimization. So this thing will be will pop up over and over, so it's good to keep that in mind. But we are actually currently at the moment more over this side here, where we have the photometric calibration, like the gamma curve and the vignette. And we will use that later in the photometric undistorted to take our images and modify them in such a way that they ideally have an equal brightness over the whole image sequence, which will not be possible, but at least we can adjust every single image to have a constant brightness. That's one important step for this algorithm to work. So having a photometric calibration is useful. Okay, let's go back to the NumTypes here and let's save that. So this is the maximum residuals per point. And with this constant variables, we can now try to find easier ways to define our matrices, our vectors, and we will do that by defining several type defs here, a lot of type defs actually, and we will start with the double matrices. Then we will have the float matrices, and then I believe we'll have the vectors. So with the eigen library, we have the matrix data type. And this matrix data type will take a type name. That could be, for example, a double. And it will take a specific identifier for, in this case, the rows and the columns. For this first data type that we want to define here, the rows and columns will be dynamic. So we will have eigen again, then we'll have dynamic, and next we will once again have eigen and dynamic. And we will call this data type by met for matrix and then xx for the unknown number of rows and columns. And we will finish that with a type def. And this is one of such type defs that we will define here. Next, we will go on and define quite a few more. The next one is, again, a double, but then the other two parameters will be fixed using the cparse variable that we defined above. And we will call that one matrix CC. Then we will have a matrix with cparse and 10, which will be met C10. Then we will also have a matrix with 10 rows and 10 columns, which will be a met 1010. Then we will have a matrix with 13 by 13 entries, which is a met 1313. And now we'll continue with the same scheme with 8 rows and 10 columns, which is a mat 810. Then we will have 8 and 3 parameters, which is a mat 8.3. Now I need to pay attention to not get confused here. Mat 8.3. 8.3. Okay. Next we will have a matrix 6.6. Mat 6.6. Then we will have a matrix with 5 by 3, which is a mat 5.3. 5.3, then 4.3, then 4.2, 4.3, 4.2. Next we have a 3 by 3 matrix, a very important one, which is mat 3.3. Then we have a mat 2.2, 2 by 2. And then we will have a matrix that has 8 rows and cparse columns. That one is called mat 8c. And now we have vice versa. We have cparse, comma 8. That is C8. Then we have a matrix which has 8 by 8 dimensions, mat 8.8. After that we have a matrix with 7 by 7. We have 4 by 9. We have 8 by 9. We have 9 by 4. Nine by 8. 8 by 1. 8 by 1. Then 1 by 8. After 1 by 8 we have 9 by 1. And we have 1 by 9. Then we have 8 by 4. And of course 4 by 8. Then we have 4 by 4. And then we have 14 by 14. And lastly we have 8 plus cparse plus 1. And we have 8 plus cparse plus 1. That's it for the double matrices. Now we need to fix the names. So we have a mat 8.8, a mat 7.7, a mat 4.9, a mat 8.9, a mat 9.4. Then we have a mat 9.8. Then we have a mat 8.1. Then we have 1.8. 1.8, 1.8, 1.8. It's really hard to concentrate. Mat 1.8, then 9.1. Then 1.9. Then 8.4. 4.8. for 4. So far, this is exactly the same as the original code, if I'm not mistaken, of course. Then we have mud 14, 14. And the last one is mud PC, PC. Okay, I think we have everything. Let me just double check. 8.3, 8.10, 6.6. Okay, that should be fine. Let us now continue with the float matrices, because it's so much fun. So we can just go ahead and do the same with the float matrices. It's unfortunately not exactly the same. So first of all, we need to change the double to a float. And then we have, it's starting with the 3x3 matrix, which is then called mat33f in this case. Okay, let's create some of them and let us change that. So we have 10 by 3, 2 by 2, 3 by 1, 2 by 1, 6 by 1, then we have 8 by cpars, and we have cpars by 8. Then we have 1/8. Then we have 6/6, 8 by 8, 8 by 4. Then we have 6 by 6. Then 4 by 4. Then 12 by 12. 13 by 13. 10 by 10. Next we have 9 by 9. Then we have 4 by 2. Then we have 6 by 2. And we have 1 by 2. Then we have a dynamic version. So we have eigen dynamic. And once again we have eigen dynamic. Then we have our combination again, 8 plus cpars plus 1. And we have 8 plus cpars plus 1 again here. And lastly, we have the dimension 14 by 14. Okay, let us now fix the names. We have mat33f, then we have 103f, then we have 22f, and then we have not a matrix but a vector, vec 3f. Then we have once again a vector, which is a 2f. In this case, it's a column vector, because here we have the rows and here the columns. 6 by 1 is again a vector, vec 6f. Then we have a matrix again, mat 8cf. me just continue the music. Then we have mat_c8f. Then we have a mat_18f. Then we have 66f, 88f, 84f. Then we have 66f, 44f. Then we have mat1212f, 1313f, 1010f. This looks very cryptic, but in the end it will help us to write less code. This is a mat99f. Then we have a 42f, a 62f, a 12f. This dynamic matrix is mat_xxf, and the cparse matrix is a mat_pc_pcf. And lastly we have mat1414f, and this is it with the float matrices. Easy. Next we have the vectors. There is a double vector section, double vectors, and there will also be float vectors later. And there will also be one unsigned char vector. And there will also be a vector of eigenvectors later. So double vectors will be not float but double here. Then we have cparse, and the last parameter, the column parameter, will be 1 for every definition, and this one will be vec_c without the f. And now we can copy that and create the remaining vectors. So we have a vector with 14 rows, one with 13 rows, one with 10 rows. Then we have 9 rows, 8, 7, 6, 5, 4, 3, 2. Next we have one dynamic vector. And lastly we have once again 8 plus cparse plus 1 dimensions. And this is it with the double vectors. Now we need to fix the names. Vec_c is correct. Then we have vec14. Next we have vec13, vec10, vec9, vec8, vec7, vec6, 5, 4, 3, 2. Then we have a vec_x, and we will have a vec_pc, and that's it for the float, for the double vectors. Next we have the float vectors, which seem to be different. So let's write them from scratch. Let's change this double to a float. Then we'll have this one, definitely. This is the vec PCF then. But we will also have different vectors. The first one is a cparse vector, which is called vec_cf. Then we have one with max res per point, which is the vec_nrf. Then we have 12 rows. Next we have 8 rows. Then we have 10 rows. That's really chaotic here. Then we have 4 rows. Then we have 12 rows. 13 rows. 9 rows. Then we have eigendynamic. Then we have this 8 plus cparse plus 1. And lastly, we have 14 dimensions. Okay, let's rename the type names. So the first one is vec_cf, that's correct. And we have vec_nrf. Then we have vec_12f. Then vec_8f, vec_10f, vec_4f, vec_12f, vec_13f, then a vec_9f. Then we have vec_xf, and we have the PCF, and lastly we have vec_14f. Okay. Now the unsigned char vector. This is a type def from vector with a vec2. Oh, sorry, that was wrong. Sorry about that. It's a matrix. So it's a type def eigenmatrix. Then we do not have a float, but an unsigned char with 3 by 1 dimensions. And this will be called the vec3b. Which seems to be a vector that represents the RGB color, probably. Let's put that here. Maybe RGB pixel color, pixel intensity. Okay, next we have a vector of eigenvectors. Here we define the vector. So vector, including the type vec2 that we have defined above. Vec2. Then we have eigen aligned allocator of data type vec2 as well. And this will be called vec2. And those are the double variants. We will have a vec3 as well. We also need to change the allocator to vec3 and the name to vec3. And then follow the float data types, we have a vec2f and a vec3f, with the allocators also pointing to the float variants, and names will also end with f. So the 2D vectors and the 3D vectors are the mostly used data types that we will have in our program. And lastly, we will add a debo vocabulary. And this will be a type def from debo3 vocabulary. And this will be called op vocabulary. Like this. Something's not working here. I hope this will be fixed in a minute. For now, let's leave it like that. So we have a vocabulary in the end, and these type definitions that we have here will help us to write less code, and they give us an idea of what kind of dimensions we will deal with in the code. Okay, let's save that and let's see where we are using it in this GlobalCalib header file. It is weird that now there's an error, but let's just try to recompile. This is working. Let us quickly delete the build directory. Maybe there's an error here. Move to trash. Okay, ziplib is not found, weirdly. Okay. Okay, I have no clue why this error is still here with the NumTypes. It usually should be fine. Okay, but I do not see any error at the moment, so let's continue. Next, what do we need? We have a GlobalCalib.header file, but we also need one implementation file. That is, we need to somehow fill up those variables here. And this will be done in the setGlobalCalib function. And this, of course, needs to be implemented. So let's create this file in the source directory. And we need to keep the structure. So also in the source directory, we need to create another folder, new folder, and then we call it internal. And in this folder, we will create a new file, which is called GlobalCalib.cc. Okay, in this GlobalCalib.cc file, we will include the header file. Include internal and then GlobalCalib.h. Here we will use the namespace LDSO, and here we will create another namespace called internal. Okay, that's weird. Oops. Okay, messed up something. Okay, let's now keep it like that. Okay. So here we will copy the code from the GlobalCalib header file, namely the variables here, and define them here without the extern keyword. All right. So this stays the same. We need to define them here. We have a matrix 3F. And then we have the floats. And what is missing is our function void set global calib, which takes in the width, a height, and a constant calibration matrix of type eigen matrix 3F and K. And here we will open the implementation body and we'll implement this function. This function will be used in the dataset reader. So let's search for it. Set global calib. So when we call the set global calibration method here, it will call the global set global calib function and pass the parameters that have been calculated here. And therefore, this is one important function that we will implement now because it will be used in the dataset reader. Okay, how will this work? In a nutshell, what we will do, we will calculate how many pyramids we can get given the image dimensions, so basically the width and the height here. This will help us to calculate how many image pyramids we can get. An image pyramid works like this, so we have the width and the height, and it always divides those two dimensions by half. And while this is possible, we will create new pyramid levels. If this is not possible, then we need to throw some errors. Yeah, but this way we can prepare the data, the data structure here. And next we need to fill this data structure. So this is what the setGlobalCalib function will do. We start by defining an integer of w level is equal to w, and an integer of height level is equal to height. Then we define a variable which is called permit levels used. This will be set equal to 1. Okay, let's save this. Next we have this while loop with the condition of testing if w level modulo 2 is equal to 0. So we will test if this variable, which could be, for example, let's write it here. This could be 800. Height could be 600. So therefore, we can divide that by half. So this is 400. Then we have 200. Then we have 100. Then we have 50. Then we have 25. And here there's a problem because dividing that by 2 will yield 12.5 or something. And this will not be possible. So in this case, would have 1, 2, 3, 4, 5, 6 permit levels. But of course, this can also fail for the height. So this will be 300. This will be 150. And this will be 75 if I'm not mistaken. And then we have a problem because modulo 2 will not work, or let's say not be even, or something like that. So this is what we will test here. So we test the condition for w level modulo 2 is equal to 0, and of course h level modulo 2 is equal to 0 as well. And next we will test w level times h level is greater than 5000, and permit levels used is smaller than permit levels. And these are our conditions. It should be true all along. And if this is the case, then we go ahead and we divide the the w level by 2. W equal divided equals 2. We do the same with the height level. And then we use permit levels used plus plus. And this will repeat until this condition is false. And this way we calculate our permit levels that we can use. After that, we print out how many permit levels we are using. So I will do that with the log, I think. How was this written again? Log debug maybe? Let me quickly double check here. Log warning, log error, log info it should be, I think. Here. Okay, I just forgot that. So log info. We are using pyramid levels 0 to, then we have pyramid levels used -1, and next we say coarsest resolution. Coarsest one is W level times height level. Don't forget the exclamation mark and an end line. Okay, let's reorganize that so we can read it in one go. Okay, next we have a condition. If W level is greater than 100 and H level is also greater than 100, which should be pixel here in this case, then we want to print out a warning. So let's log a warning. Something like that. That is that we are using not enough pyramid levels, and we should consider scaling to a resolution that is a multiple of a power of 2. So this is why you will see image resolutions that are powers of 2, as they can be divided easily using this half scaling within the image pyramid. We also need to check if we have enough image pyramid levels. So pyramid levels used, if this is less than 3, then we want to print a warning as well, which will tell us that I need higher resolution and I will probably segfault, which is a very nice information, especially if then we will get in fact a segfault, a segmentation fault. So this will be a helpful message to get to know the reason why we have the segfault. Okay, if this is done, then we need to continue with the WM3G variable. This will be set to W -3. And the same with the HM3G variable, which which will be set to height -3. Now we will prepare the variables. So that is, we set the initial values for W global at pyramid level 0. So this will be the finest level, so the level with the most resolution. This is equal to simply the width. Then we have the height global 0. This is equal to the height. And we have the K global 0, which is equal to the K matrix, the calibration matrix. Then we have the individual variables. For example, fxg is equal to K 0, 0. So the K matrix, let me just write it here, maybe. So K is equal to, could say we have fx here, then we may have 0 here, we have cx here, then we have fy here, we have 0 here, and here's cy. So this could be a sample calibration matrix, could look like that, where we have the fx, fy, cx and cy parameters here. And now we need to extract them from the calibration matrix. So we need to set the fx and fy global, and also the cx and cy global, namely to K00, K11, then K02. So the second or the third column in this case, and the second row and the third column, so K12. Next, now we can see that the KIG at level 0 is equal to KG at level 0, and then dot inverse. So the KIG is actually really the inverse. So let's go back to the header file. And where did I write that? This is the inverse pinhole camera model. I think I wrote somewhere that the I could be the inverse. I just want to correct that. Maybe in NumTypes. Okay. Not sure where this was. I will find that, I think, later. Maybe I didn't write it. Okay. Let's go back to the CC file. Now we have the K inverse global variable, So we can define fx, fy, cx, and cy for the inverse parameters as well. By just taking the k inverse global here and extracting the parameters. But of course we also need this index here, because that's an array. And this way it should be fine. So here we fill up the non-inverted and inverted camera intrinsics. And that is for the first or for the finest level. And here below, we fill them up for the remaining levels. So, as you might know, we need a for loop. We loop through the levels, an integer level. We start at level equals 1. We check if level is less than permit levels used, and we increment the level. Simple as that. Next, we need to fill up or fill the data here. Width global at the current level. So in the beginning this will be 1. This is equal to w to level. So w is an integer. So this is basically a shorthand notation for division of width by 2. I think it's a bit shift operation. Pretty nice technique here, I have to admit. And for the height global level, we set height, then bit shifted using the level. Which is equal to the division of height by 2. And that's all about the image dimensions. Next we have the intrinsics. Let's comment that here. We have the fxg at level. This is equal to, now it's not that fancy, fx global at level minus 1. So we take the previous level, the fx global from the previous level, and we simply scale that by 0.5. It should also be possible with a bit shift operator, but I'm not sure this fx can be a double and then it's not working, I think. But it does the same as we want, so let's keep it like that. Fy global is equal to Fy global level minus 1 times 0.5. So this is basically the division of Fx and Fy by 2. And next we have the Cx and Cy. And this is equal to a little bit more complicated in this parentheses here, Cx g at level 0. We add 0.5. So we shift it by half. And then we divide, cast it to an int, 1 bit shifted using level. And the result will be shifted by a negative 0.5. So we shift it positive by a positive number, we divide it, and then we shift it back. Not sure if I understand it correctly at the moment. I need to think about it. So let's continue with Cy g 0 plus 0.5 integer 1 bit shifted using the level, negative 0.5. And this is the principal point. Then we have the complete calibration matrix we need to set, or we need to build in this step. So k global. And this is not the shift operator, but this is actually the initialization operator, I would say, for a matrix, which takes in the first row, which is fxg at this current level. We defined it in line 82. Next we take 0.0, then we take cxg at the level. So this is the first line. Then we have 0.0, fyg at level, and then cyg at level. And then we have 0.0, and the last one should be 1. There's a comment, synthetic, whatever this means, synthetic. This is a comment from the original code base. I'm not sure what this means, synthetic. Okay. And this one here, this line, is exactly what I have written here. This is the form of a calibration matrix, and this will be set here. Next, what is missing is the inverse, k inverse global at the current level. This is equal to k global at the level, and then inverse. And by calculating this inverse, we have all the components that need to go into the x, fy, cx, cy, but the inverse here, fxig, fyig, cxig, and cyig at their current level is equal to the kig at the current level, and then the coordinates at 0, 0. And similarly, we continue with the other entries. So this is 1, 1 here. This is 0, 2. And this is 1, 2. And this is the complete function set GlobalCalib. So let's save that. There's still this error here. We try to fix that by adding this GlobalCalib.cc file into our CMakeLists file. Let me quickly find that. Okay, I found it. We are in the source directory. Here is a CMakeLists file. And here we have the feature.cc file. We have the settings.cc file. And we now also need the internal / GlobalCalib.cc file. And this should be everything. And now let's see if this compiles. I have a bad feeling. And my feeling is correct, because I forgot a semicolon, as usual. And I have a typo here, it seems. Okay, hopefully things we can easily solve. All of them are in the NumTypes header file. Let's find that, NumTypes. Okay. Here we have the dbo3. This should be a capital W. Okay, now it has found that. Then I think the others are in the GlobalCalib. Yes, GlobalCalib.cc. Here there's a missing semicolon, obviously. And permit levels used, there's another missing semicolon here. Okay, let's save that and let's try to recompile. Let's move it a little bit further to the top. Oh, it's working too long here. Oh no. Okay, it's working, it seems. Which is weird. Why is there an error here? Okay, that's the problem with the eigen name. Internal GlobalCalib.h. Internal GlobalCalib.h. Which points to NumTypes. Weird. Let me quickly try if I can change that to eigen. Still works. So there's some error with my IDE, with the Visual Studio Code, it seems. Or I cannot put my finger on the reason at the moment. But I will try to solve that off camera, because it's a little bit annoying to see that. But I think in general we should be fine here. Let us go to the dataset reader now, and let's try to use that function with the set global calibration. Let's put this comment here. What about this get calib mono? Where is this defined? It's here. And we need the undistorter for that. Well, not necessarily. Can just move this here. And this here. So even though we have those squiggly lines here, we should still be fine for now. Let's try to compile that. No, there's an error. Set global calibration. This cannot be found, and eigen can also not be found because we are missing the includes probably. Yes. We can get rid of this global calib here. And probably of global funcs as well. Even though we did not finish that yet, but let's try to recompile. Are there errors or not? Ah, okay. So here it is expecting the LDSO internal namespace, which we have commented out here, like this. So let's get rid of this to-do. It's always nice to get rid of to-dos. And then the error should be gone. And this should work. Okay, now I would like to use this this method as well from the dataset reader. This set global calibration. Let's see if we can get that to work in this example or in our main function. Let's scroll up a bit more maybe. Get num images. I think we could call this set global calibration now. Let's try that. And let's try to recompile. That seems to work. And now let's do the final test. Not the final test, but the big intermediate test. That is, we want to run the SLAM. So this is the shell script here, run LDSO Twitch sequence. And there's an error, cannot read zip archive. Okay. Yes, that's true. Okay, this is weird because last time I think this worked. And now there's an error. Let's check the which file. Which file is the reason for that? So here we have libzip. And libzip is not found. So this error is showing up when we compile. So when we compile not found ziplib. Compiling without zip capability. Let me check if this is working with the original code. LDSO. Make project. This might take a while. Oh, this will probably take a long time. Okay. In the meantime, let's continue. So we can at least compile, but we do not have the zip lib. And that's why we cannot use the dataset with the zipped archive. So what we should do is go into the vslam datasets and unzip the images here. We can do that. Which may also take a long time. Okay. So in the meantime, let's continue with the other file. That is the global funcs header file. Global funcs. Okay, and this will be a header only file, so this will not have a corresponding CC file.